Okay, so today we will be talking about quantum mechanics, and we will be talking about the, the first of all, let's start with the simple quantum mechanics, that nature of light. Nature of light. Okay, we know that nature of light is in two forms. One is wave, and the other one is particle. Okay, and waves. What is waves is light moving in the form of oscillations. Okay, and these oscillations are also known as, the second name of it is, second name second name of light is uh, electromagnetic, sorry, magnet ah magnetic waves. Okay, that's our first clue, first definition of waves. And remember that no matter it's either wave or particle, the speed at which it will travel, it will be the same, 3 meter per second, 3 times 10 to the power 8 meter per second, and this value is a fundamental constant, fundamental constant or law. Okay, and coming to the, and one more thing, while we are at it, let's talk about even not only light, but particles can also act as wave and particle, like electron. So what we will say about that is, if electron is acting as a wave, because mostly whenever we are doing quantum mechanics and we want to study the behavior of quantum particles, we mostly take electron as our study material. Study material. Now, what do we want to? What I want to say is, if we want to find where could it be on a certain area or certain place, like the where a particle could be found, for that we would take the square of the current wave. Okay, which in terms of mathematics is written as, quantum mechanics is written as, norm of uh, uh, psi. Okay, remember that this we do to normalize. Okay, this is something, there is something known as normalization. For that normalization, we could write it as integral of psi norm square d of x equals to 1. So this, what we did here is, we normalized it, normalization. Okay, and this normalization turns is one more thing. Yeah, so while now we know that when when we don't observe, sorry, when we don't observe, we know that the particle, or that particle is in superposition. superposition. Okay, so I would be saying the particle exists here, here, here. Every single place you can think of, it would be there. Okay, and what we do is, when we observe it, okay, when we observe it, the particle now has a certain point. Okay, now changes when, sorry, changes when observed. Okay, then this is normalization. This will, what this does is that whatever the probability we get, all the sum of all the probability, all the positions, whatever sum of all the possible paths, not position, possible path should equal 1. That's what normalization is about. Okay, now this was all about waves. Even we will study more at further on, but then particles. What about particles? So particles, in this, now light is acting as quanta of light, smallest unit of light. They are quanta of light. What does quanta of light mean? It means that each particle is now even the second name of quanta of light is photon, and now each particle is in each now light is acting as a particle, single entity. Okay, now for the evidence of particles, the best evidence is the photoelectric effect. We introduce photoelectric effect. First, it was there were 2 times when this experiment was done, but Einstein was the one who completed this experiment in such a way that the answer that he got the Nobel Prize for this theory. So what his theory said is that light in terms of particles, when light will be in terms of particles, what will happen is, when light will be in terms of particles, what will happen is the electrons in the metal, this is a metal, when light, wait, let me just add one improvement in this. Okay, yeah, so imagine these as quanta of light. So what we do is, when each quanta of light hits the particle, if that quanta of light if that quanta of light has energy more energy than uh, the binding of the electron, the amount of energy which is in the bond between the electron and the metal, if it's more than that, the um, the electron will bounce off with enough sorry with enough kinetic energy. But on the same time, if that energy is equal to the work function, what will happen is the electron will only escape. Electron will only escape. Okay, so it won't have enough energy. Kinetic energy is less than is less. Okay, is less. I would say it's less. Is less. Okay. Okay. And one more thing, the intensity I increase increase in intensity increases the number of electron released. Okay, and the frequency and the wavelength change, the frequency and lambda change will have no effect on the amount of number of particles escaping, because they will only because we're talking about a single quanta of light, single photon hitting a particle, hitting an electron, and finish. That's the only thing. That single electron will hit this electron and finish. After that, it will get absorbed. It will that this will create energy for this particle or this electron to bounce off. Okay, so that's how it will work. So in terms of equation, it is written as energy of the photon, which we write as mostly this. This energy of photon, wait, sorry, give me space here. Okay, so if hf equals to wave work function plus 1 by 2 mv square max. By max I mean maximum. We already know what 1 by 2 is. 1 by 2 is the kinetic energy. And so what we are doing is we are getting the we are making a proportion. So hf is nothing but photon energy, and that photon energy is then so what we say, this photon energy is directly proportional to sub work function plus 1 by 2 mv square. Okay, and I could write the same thing as E, because energy of photon equals work function plus k dot E max. Okay, because energy or kinetic energy will be the max. Even if it's minimum, it will be at its maximum, the amount of energy given to the kinetic energy given to the particle. And so this is wave function. It's also known as binding energy. Binding energy, that's what work function also is. And this energy over here could be written in terms of joules and electron volt. Okay, so electron volt, how, if let's suppose if we have let's suppose if we have energy 1000, if we have energy, okay, in terms of joules, okay, what we do is we could convert it into electron voltage. How? we will do energy times 1 over 1.6 times 10 to the power minus 19. And yes, you are correct, this is nothing but the charge of charge of electron. Perfect, good. And mostly we ignore the negative part, okay. And what we get is, we get the same energy, the energy which is in joules, now we get in terms of electron volt. Vice versa for the joules as well. What we do is that now we are making, we want joules, right? So we do EV 1.6 times 10 to the power minus 19 equals to joules. So we just make joules the subject now. This is the energy conversion from joules to electron volt and electron volt to joules. And so this experiment over here is very useful because um, it's nowadays applicable to many of the areas, okay. One thing, we might there might be questions being asked by the people or students, like, will there be a point when maybe, because these questions can come, maybe in the thoughts of the people, maybe, is it possible, because it came in my mind as well, and I was like thinking, could it be the reason, could it be that it's possible, maybe is it possible that the metal, because we know that the amount of, even if I sit and calculate the amount of electrons being bounced off, let's suppose if I, for that I could do this, energy N equals to HF. So if I'm right, this, if I do N equals to HF over E, okay, HF over E, okay. So can, first of all, let me finish the question. Can, is it possible that we may run out of electrons, that the metal may run out of electrons, out of electrons, okay. But that is a good question, it's a very like very good question, but then the thing is, the amount of electrons, the amount of electrons being made, the amount of electrons that the metal will have are more than, are more than are are more, also that they are being generated every time more and more. So the amount of the generation of electrons is very fast, okay, even faster than the electrons or the photons hitting them, okay. And so, wait, this, does this work? Wait, let me see. um so n is a constant, right? It's an integer number. N is an integer number. N is an integer number. So if we, is it possible, so is it possible to get photons? So is it possible we could rearrange this? Yes, it is possible. How could we do this? We will do E over N equals to HF. So E over HF is equal to N. This will give us number of photons. If I am right, yes, it will give us number of photons. So we could C uses. Okay, let's pause. Now we know that if we are given a situation in which, let's say they give the energy of photon, not I mean in of course it's higher grade, so they won't give it exactly the same. There will be some twist, sorry, and they told us to get the kinetic energy of the electron. So if we will, let's first of all visualize how what does the question mean. So the question is trying to say that if light is coming in terms of photon, is coming here and hitting this metal, okay, so what the question is, the photon with certain wavelength or certain frequency hitting this electron, what will be the speed of this electron after bounce, after uh, collision. I think collision would be a good word to say. So yeah, because now here your common sense should say that the amount of voltage velocity will be a lot. Okay, if it's a lot, that means your answer is right, but if it's less, just know that there might be something wrong. Okay, so that what this equation can give. If we rearrange, or if you want me to rearrange, I could rearrange as well. Minus this over, not over, this would be 2m, or not 2m, this goes m down, m goes down here, so 2 is equals to square root of v. So this would give us the velocity of electron. Okay, now wait, did I just spend so much time explaining only the two phenomena of light? Look, that's what is interesting about light. Even though it has only two nature, even though it's like everyday life used, but still it has such a nature that it takes so much to explain it. Okay, now let's get using this particles, everything. Let's study one more topic known as Heisenberg's uncertainty principle. Okay, now Heisenberg's uncertainty principle says that if you know the position of a certain particle, you are less aware of its uh, less aware of its momentum. Or I would just let me be careful. Let me just write it as in terms of, okay. So this is what the momentum would be: less aware, aware, less aware, less knowing. Okay, know that I'm not saying I don't know its momentum or its the velocity which is it is moving at. I didn't say I don't know it at all. I said I'm less aware of it. Means the accuracy. Let me write the equation. The accuracy of measuring of the momentum decreases. Okay, that's what I'm trying to say. So this downgrades the accuracy or the preciseness, the downgrades, and this one upgrades. Yeah, and the more I know about its the momentum, the less I know about its position. So it's the opposite now. and so and so that's what it was about. Okay. Okay, one more thing, the interesting phenomena of light also, that we know that light travels in terms of electromagnetic waves. Again, I'm talking about waves, electromagnetic waves, magnetic waves. Okay, we know that in electromagnetic waves it travels in this way, right? Okay, now we could polarize it. Polarize. Okay, now how could we polarize it? I think it's SZ, not S I, sorry, IZ. Okay, polarize. Now polarize, it's in two directions. I think I didn't clarify that one properly. It's two directions. Okay, this is how it was, how this is how it will move. Okay, what polarization does is, if we had the two types of polarizers, vertical and horizontal. Now depending on its angle we could change it into also a diagonal. Okay, now what we do is, this is a vertical and this is a horizontal. Now, and this is a diagonal. It's a 45-degree angle. So what it does is, if it's a horizontal, it's a horizontal, it's a horizontal polarization. Only the horizontal part of the light will pass and this one will get cancelled. If it's horizontal, only this one will pass, only this one will pass and others will cancel. And here it's 50-50, here's 50-50. Okay, now let's suppose um, so let's suppose we know that when we put this polarization, what polarization does is decreases the number of photons going through the material, going through in a certain way. What I think in terms of photons it does is, uh, in terms of sorry about the writing, in terms of photons, it's decreasing the number, not okay, let me clarify, sorry, the probability of number of photons going through. Okay, so let's suppose in terms of um, like this and this, right? So I could write it as the light before light before light before is equal to the light. This is what in terms of math I would take it as light sine y plus light cos y cos x is our light before. Okay, that's how it would look like. And as also that In polarization, we are again coming back to percentage added. And so again, oscillation. Oh, let's study the wave as well if while we're at it. One distance, one trough to one crust to other crust is lambda in terms of meter. And again, this is, let's have a little bit of wave mechanics as well. This is amplitude. Let me get quantum mechanics. So this is amplitude, and this is the peak, the maximum peak, minimum peak, also known as trough and crust. I won't say that, I won't be like writing it like that. And also the property of light is that light fast in vacuum, air, slow in solid, liquid, right? It will bend. Okay, and so what else do we have? Yeah, one more thing. We know that in classical physics, everything is written as the momentum is written as P equal mv, but for quantum mechanics, since it's about particles, and particles can exist in the form of, since it's about particles, P is equal to h over lambda momentum. Okay, and this is mostly written in terms of nanometers. Okay, nanometer. And when we insert this over here, we get momentum, and h is a constant, and this constant is 6.63 times 10 to the power minus 34 joules dot second. This is our constant. Okay, and what else? Yeah, so waves, nature, and that's why this is used. Also, what I thought of is, I suppose, why not combine these two as well? Like, if this equals lambda is nothing but e or h. So how about writing it as like this? Wait a minute. Lambda is e over h, right? E over h, and when it goes up, so we could write it as over h. Yeah, leave that. We'll not do that. And so, one more thing, last point. To find the particle in a certain region, what we do is that we take the integral of the psi in that region, the amount of this dimension, and when you get the dimensional equal to 1, we get the 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 position of where we could find the particle. Okay, but we never find it. We always get out of the point where it will be found. We'll get it out of somewhere else. We'll get it from somewhere else. Okay, yeah, that's it. Thank you.